Today's video involves the solving of systems of quadratic equations. Recall from Algebra 2 that systems of equations involve multiple equations with multiple unknown variables. There are a few different methods of solving them. One is called the elimination method. That's what we're going to practice in this video. You can also do the substitution method, solving for one of the two variables and then substituting that equation back in to the original equations. You can also do them graphically because systems of equations involve finding the intersection points between graphs. Certainly your calculator is capable of doing that, Desmos is capable of doing that, but oftentimes it is an estimate when you're using the graphing method of solving a system of equations. The elimination method that we're going to use today in our example is an effective algebraic method for finding the exact points that are in common between two equations or two graphs. Systems of quadratic equations could include any combination of circles, ellipses, parabolas, and hyperbolas. And take a look at the diagram on the left. You'll notice that these conic sections can intersect anywhere between 0 and 4 times. The two conic sections could not intersect, like this one here. One of the conic sections could be tangent to the other. Imagine if this ellipse was tangent to the circle, if they just touched at one point. They could intersect in 2 points, like these guys. You could also have a situation where they intersected in 3 points. Imagine a hyperbola that touches 1 time on one side and then 2 times on the other side. And then above you'll see 2 examples of when 2 conic sections could intersect 4 times. So there are lots of different combinations. Certainly if you graph the 2 conic sections you can see exactly how many times they're going to intersect. But our algebraic method will also show us all of the possible intersection points. When solving any system of equations, our goal is to go from 2 equations and 2 unknowns down to 1 equation and 1 unknown. Again, there are those 2 algebraic methods, elimination and substitution, that allow us to do that. In this case, this pair of equations is ready-made for elimination. You'll notice that the y-squared terms are literally lined up, one above the other. The elimination method allows us to add 2 equations together or subtract to eliminate one of the variables. In this case, you'll notice that y squared in the second equation is the opposite of negative y squared. So when we add them together, the 2 equations that is, we are going to eliminate the y's. The y's are going to cancel each other out. So imagine we're adding here 16x squared plus 0, because there is no other x squared term, so that's 16x squared. Negative y squared plus y squared is 0. 16y plus negative 16y is also 0. That y has been eliminated. There is no x term in the original equation, so 0 minus 48x. And now the constant terms. Negative 128 minus 32 is negative 160. Adding on the right-hand side, 0 plus 0 is 0. So notice we have taken 2 equations with 2 variables, and now we have 1 equation with 1 variable. And we can solve this equation using all of the methods that we learned about in our polynomial unit back in Chapter 2. I'm going to start by factoring out a common factor of 16. It makes life a little bit easier. Now I'm left with x squared minus 3x minus 10 is equal to 0. This polynomial is now factorable as well. We have 16 times the quantity x minus 5 times the quantity x plus 2 is equal to 0. So that means x can be either positive 5 or negative 2. Now we're not finished. We've just found the x values of the solution to this system of equations. Now what we need to do is take these solutions for x and plug them back into one or the other of our original equations to find the corresponding y values. On the previous slide we found x is equal to 5 or negative 2, so I'm going to go ahead and plug those in. I'm going to plug them into the second equation because you'll notice that's just got that 48x, so I'm going to start with y squared minus 48 times negative 2 minus 16y minus 32 equals 0. Y squared minus 16y, the negative 48 times negative 2 is a positive 96. Positive 96 minus 32 is a positive 64. And again, this is factorable. Y minus 8 quantity squared is equal to 0, so y must be 8. Now remember what this means. We plugged in the x value negative 2. That implies that the y value will be 8. This is a solution to both of our original equations. The ordered pair negative 2, 8 solves both of them. It also appears on both of their graphs. It is an intersection point. Now what we need to do is also solve for the values if x equals 5. We're going to do the same thing. Substitute for x. Y squared minus 16y again. This time we have negative 48 times 5 minus 32, that equals negative 272, is equal to 0. To solve this equation, I'm going to use the quadratic formula. Y is equal to the opposite of b, so that's positive 16, plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. That's our quadratic formula. Underneath the square root, all of that calculates to 1,344, and all over 2 still. 1,344 is the same as 64 times 21. 64 is a perfect square. So we can simplify a little bit further. The square root of 64 is 8. That'll be on the outside. And the other factor of 21 is left on the inside. And the division of 2 applies to both terms. So we are left with y equals 8 plus or minus 4 times the square root of 21. Remember, those are the solutions for when x is equal to 5. So that gives us 2 ordered pairs, 5 and then 8 plus or minus 4 times the square root of 21. We have a total of 3 solutions. Remember, these 3 ordered pairs are solutions of both of the equations and represent the points of intersections between the 2 conic sections, the hyperbola, the first one, and the parabola, the second one. Let's take a look at the graph. Here are the graphs from Desmos of the 2 conic sections. Notice the hyperbola, that's the first equation, and the parabola, that's the second equation that we were dealing with, and the 3 intersection points. One is at the vertex of the parabola and one of the vertices of the hyperbola, negative 2, 8. And the other 2 occur one above the other, both at an x value of 5. And the first one is 8 plus 4 times the square root of 21, and the other one is 5 comma 8 minus 4 times the square root of 21. So you can see that our algebraic method of solving is confirmed by the graphical method.